Hi, this is Sudeep and I welcome you back to this wonderful journey of learning structure analysis with StatPro. We are in the third phase of this series where we are learning how to model the material and the sectional properties. In the last two sessions, we had looked in some details about how to calculate the cross-sectional areas. In this session, we will talk about the moment of inertia. But before we do that, please do take a moment to hit the subscribe button if you are new to join us in this wonderful journey, and do press the bell icon for more notifications from this channel. You may remember that the axial deformation were related to the cross-sectional area, while the bending deformation were related to the moment of inertia. If not, please revisit session number 25 by clicking on the link above. Now, what is this moment of inertia? We will find out in a moment. So let us consider to have this cross-sectional area like this, okay, and let us choose an axis. Now let the centroid be at this point, which is represented by C, and let us consider an axis to pass through the centroidal area. Now let me sort of draw it. I think more horizontally like this. So now this is the axis that we have. Let this be represented as the z-axis. Okay. Now why we have chosen the axis to pass through the centroid would become clear when we discuss the flexure theory, which we would do in this series. But for now, just take it for granted that this axis would go through the centroid of the area. Now, let us consider an elemental area dA, which is located at a distance of y from this axis, right? The vertical distance is y from this axis. Now, the whole cross section is made up of this numerous or infinite, or rather numerous elemental areas, right? Now, the first moment of this area about this axis would be represented as, this is the first moment of the area dA would be represented as dA into y. And what would be the second moment of this area? Second moment of dA would be equal to the moment of the moment. So dA into y. So it would be dA into y square. Now, let us consider that we want to have the summation of all the second moment of all the elemental areas in this cross section, and that sum would be represented as the moment of inertia I. And since the moment of inertia, we are finding it about the z-axis, so it would be, let us give it a subscript Iz, and so it would be represented as integration of y square dA. So the moment of inertia thus can be defined as the summation of the products of all the elemental areas, or rather, let me redefine. So the moment of inertia can be defined as the summation of the product of all the elemental areas in the cross section with its square of the distance from the axis z, which is passing through the centroid of the cross section. The mathematical expression of moment of inertia is this, integration of y square dA. If there is any question or any confusion about the moment of inertia, please type it in the comment section below and I will respond to that. So now we intend to find out the moment of inertia of this rectangular section from the first principles. Okay, so how do we do that? Now, a couple of things that I wanted to discuss here is that we want to find the moment of inertia about the z-axis, which is passing through the centroid of the cross section. The perpendicular axis is y-axis. So now we are assuming this beam to bend about the z-axis. So the beam is bending in the plane of symmetry. So the plane of symmetry is if you actually draw a surface along the y-axis like this, this is the plane of symmetry for that beam, and the beam is bending in this particular axis. Now we intend to find out the moment of inertia. Now for this bending, the moment of inertia about the z-axis would be effective. Now let us consider an elemental strip here in the rectangular section, which is at a distance y from the centroidal axis z, and let the width of this particular strip be dy. Now let us consider, or let us have the second moment of this area about this axis, okay, about this z-axis. So how, let the second moment of area for this elemental strip be dy, okay, or the moment of inertia of that we are finding. It's, remember that the moment of inertia is what? Is the second moment of the area. So the moment of inertia we are finding out about the z-axis. So this elemental strip, this cross-sectional area of the width b and the depth dy, we are finding out the moment of inertia of this about the z-axis, and that is represented as di, and that would be what? dA, which is the cross-sectional area of this elemental strip, dA, into the distance from the z-axis, the square of the distance of the z-axis, so dA into y square. Now how do you calculate the value of dA? dA is, so this is a rectangle, so it will be, the width is b, depth is dy, so it would be calculated as b into dy into y square. So this is the moment of inertia of this elemental strip about the z-axis. So to calculate the moment of inertia of the whole rectangular cross section, we would need to integrate the elemental strip di. And how we can do that? We can do that by substituting, and the y would vary. So this is d, right? And remember that we are considering the measurement along the y-axis from this centroidal axis z. So this is the origin from where we are measuring. So in this case, here if we calculate, so the value of y here is 0, and it will have positive values as we go up. It will have negative values as we go down. Now this value, then the value of y here is minus d by 2, right? Since this is the total depth is d, this is 0, this is y equal to 0, here it would be y minus equal to minus d by 2, and here it would be y equal to d by 2. So then the integration has to happen between d by 2 minus d by 2 to plus d by 2. So now b is a constant term, being the width of the rectangular section. So we can rewrite this equation as integration of minus d by 2 to plus d by 2. We take out b. So now what remains is y square dy. Now, as per the basic integration rules, this would be written as b y cubed by 3 from minus d by 2 to plus d by 2. So, then we would have this as represent d by 2 here, d cube by 24, right, minus, now this is a minus value, so y cube would be minus, so this one would become plus, so it would have d cube by 24. So it would become 2b d cube by 24, or it becomes bd cube by 12, because 2 12s are 24. So this is the moment of inertia of the rectangular section for bending about the z-axis. The basic assumption here is the beam is bending in the plane of symmetry. That's our, not an assumption but a consideration, that we are considering the beam to bend in the plane of symmetry. So if the beam is bending about the y-axis, that is, if the beam is bending in a plane of symmetry like this along the z-axis, so the beam is bending like this, right? So in that case, the moment of inertia would be b cube d by 12, and we can prove this in a similar manner. So this is I z and this is I y, okay, and we can prove this in a similar manner by considering an elemental strip parallel to the y-axis and measuring the distance from the y-axis. Okay, so this is how we calculate. Now this is a very standard formulation. We would need to use this time and again, so it's better to remember the expression of the moment of inertia of a rectangular section to be given by bd cube by 12 if it's bending about the z-axis, and it would be given as b cube d by 12 if it's bending about the y-axis. Alright, now we will focus on calculating the moment of inertia of a circular section. Now, a circular section is bisymmetric. It's symmetric about both the axes with the same dimensions. So, whatever would be the moment of inertia about the z-axis would be the moment of inertia of the y-axis, and that is very clear by looking at this section. So we have that Iy would be equal to Iz. Now we want to calculate the value of either Iy or Iz. Now let us consider an elemental area dA located at a distance, or rather let us do it according, so the positive direction of z is this and the positive direction of y is this. Okay, the reason I'm drawing the axis like this, there is a reason to it, and that is something that is related to StatPro, which we would discuss further when we get into that topic of the local axis system. But at this point, just it's enough to know that the positive axis of z-axis is this, the positive axis of y-axis is this. Now let there be an elemental area dA which is located at a distance of z from the center of the circle and a distance of y from the center of the circle. So, and let this be a line which measures the shortest distance between the center of the circle and this elemental area dA. So let this distance be represented as rho. Now, by the rules of the right angle triangle, we know that y square plus z square would be equal to rho square. So multiplying that with the elemental area dA on both the sides of the equation, we would have dA into y square plus dA into z square as dA into rho square. Now, let us integrate the equation on both the sides. So we will have plus integration of y square dA plus the integration of z square dA would be equal to the integration of rho square dA. Now, what is y square dA? It is nothing but the moment of inertia of this circular cross section about the y-axis. So this is IY and this is IZ. Z square dA is nothing but the moment of inertia of this cross section about the z-axis, and that would be equal to the moment of inertia about this axis, which is the x-axis, right? So if this is the x-axis, you remember we have talked about the right hand thumb rule. By right hand thumb rule, if this is the y-axis and this is the z-axis, the x-axis has to be this. So this one would be, and this is called the perpendicular axis theorem. Okay, so we got this deduction for this circular cross section, so we just need to remember the results of it. Ix would be equal to Iy plus Iz. Okay, now let us deduce the value of Ix. Now, one of the things that you have to understand here is we are intending to find Iz. Iy and Iz would be the same in this case because they are equal. So in that case, Ix would be equal to 2 into Iz for the circular cross section. So if we find the value of Ix, then we would easily be able to solve for the value of Iz, which we intend to find by this deduction. So now let us consider this circular section. We can remove this now, and now let us consider an elemental area of this circle at a distance of rho from the center. So this is the elemental area which is at a distance of rho from the center, and the thickness of this elemental cross section, this ring section, is rho dy. Okay, so this value here is, or rather, sorry, it is d rho. okay, d rho, which is very small, infinitesimally small cross section d rho. So what would be the area of this ring now? The area of this ring would be pi into rho plus d rho whole square, which would be the area of this outer circle, minus pi into rho square, which would be the area of this internal circle. So you will get the area of this elemental ring. Now if we expand this, we would end up with, so this is the area of the ring, elemental ring. So now if we expand this equation, it would be rho square plus 2 rho d rho, right, plus d rho square minus pi rho square. So if we open the brackets up, we will have pi of rho square plus 2 pi rho d rho plus pi d rho whole square minus pi rho square. So this and this would cancel off, and this value would be extremely small, so we can neglect this value. So we remain with only one term, which is 2 pi rho d rho. Now if the moment of inertia of this elemental ring about the x-axis would be Ix would be equal to this area multiplied by the square of the distance from the center. So it would be 2 pi rho d rho into rho square. So this would be 2 pi rho cube d rho. Sorry, this is the moment of inertia of this elementary ring only. So it has to be represented by dix. So then what would be the moment of inertia of the full cross section? The radius rho would need to vary from 0 to r. Now let us say that the radius of this circle here is r. So this is the radius. So the radius is equal to r, or we can even express this in terms of its diameter, where diameter would be equal to twice of r. So the moment of inertia about the x-axis then would be given for the whole cross section would be given as integration of dix, which would mean that we need to integrate this expression 2 pi rho cube d rho from 0 to the radius r, which 2 pi is a constant term, so it will come out of the integration expression. So we can express this now as 0 to r, and we will have this as rho cube d rho. So by rules of integration then, we have this as 2 pi rho 4 by 4, 0 to r. And now if we express this, we get this as pi r by 4, r to the power 4 by 2. So this is the moment of inertia. So the moment of inertia about the x-axis, right, about this axis, is represented by this expression pi r to the power 4 d by 2. Okay, so now let me wipe off this deduction here, and we just retain what we have derived, that is our Ix is represented as pi r to the power 4 by 2. Now r is the r can be represented as d by 2, where d is the diameter of the circle. So then we have Ix equal to pi d to the power 4 by 2 into 2 to the power 4. So it would be pi d to the power 4 by 32. Now Ix is represented as twice of Iz. So the moment of inertia about the z-axis is half of what you have calculated for the x-axis. So then we could represent Iz as half of pi d to the power 4 by 32, or in other words, the moment of inertia about the z-axis can be written as pi d to the power 4 by 64. So pi d to the power 4 by 64 is the moment of inertia of a circular cross section about its z-axis, which passes through the centroid. Now this again, this expression is another standard expression that students need to remember to derive the value of moment of inertia. So we now see how we can calculate the moment of inertia of simple shapes like a rectangle or a circle using the first principles. However, it's not that straightforward for a composite section, but we will see more of it in the next session. If you have indeed liked what we have shown today, please hit the like button and do hit the bell icon for more notifications from the Structural Insider channel. See you in the next session. Till then, bye.